Okay, this is going to be your lecture help for Chapter 10, Chemistry 1412. So, in the beginning of this lecture, he talks about intermolecular forces. These are the forces that are in between the molecules. So you have a molecule here and a molecule here, and it's the right there, the intermolecular forces. So, with that being said, intramolecular forces is the bonding within the molecule itself. So when you're looking at this diagram here, you've got a molecule of A and B, a molecule of A and B, a molecule of A and B, and so on, right? Well, the intermolecular forces are the bonds that come between the molecules here. And this, when this happens, this is like building something up, right? You're building a bigger substance. But here, this is the intramolecular force, the force between the inside of the molecule. So like hydrogen and chlorine. And together they make hydrogen chloride. But this would be hydrogen and chlorine attaching to each other with intramolecular force, and then hydrogen chloride attaching to another hydrogen chloride would be intermolecular force. Now moving on over to here, this is his example. He has hydrogen chloride. And you can see that the kilojoules per mole here are 432 kilojoules per mole, when on this side, the bond between the hydrogen and the chlorine here is 20 to 30 kilojoules, significantly lower. And that's just showing that the bond here is extremely weak compared to the bond here, which is extremely strong. And if you look down here at the diagram, you'll notice that this is way bigger than this one. They're just different colors, but the chlorine is the way bigger one than the hydrogen. And this has to do with its electronegativity, which we'll get into in a little bit. This one here is just showing you a little more, drilling it into your brain, that the intermolecular attraction or intermolecular force comes from between the molecules. A hydrogen chloride attaching to a hydrogen chloride is a weaker bond, while the bond in the middle of the hydrogen and the chlorine is an intramolecular attraction. And it is stitched together here to show you it is an intramolecular attraction. You might want to figure out a way for you to remember that if you have issues, because that is important and helpful going forward through this course. This one, I'm not sure what you've been through as far as notes and things in previous classes, but I'm just going to pretend like you know nothing so that we can just talk about everything. So the delta positive and delta negative are partial charges. That's the main thing to remember about them. It's used to indicate the quantity of charge is less than 1. And you really don't need to remember as much as you need to know that when a partial charge is negative, it's going to attract electrons over the positive charge. So when you have like something like oxygen, it's a negative charge, and hydrogen has positive charge, a positive charge. The electron is going to be pulled towards the more negative side, and that creates a dipole moment. And when you see this arrow here with the line, that's just, it symbolizes the direction of where the electrons are flowing, and it will always flow towards the more electronegative atom. In this case, because hydrogen is here, it's going to flow towards that oxygen that way. So the delta plus means a partial charge and a positive charge with less electron density. If you think about less electron density, it's less electron dense because it is more positive than negative. Creating that positive symbol means less electrons. When it's more electron dense, it's going to have more negativity. So that's what all of that means. So moving on to the electronegativity chart, you'll see that it goes from a low to a high, going from left to right. the electronegativity will always flow in this direction from left to right, and will also flow from, as you go down the chart, it will get less electronegative. And we're going to get more into it, but just like a quick note on it is because as you get lower down here, you have more electron shells, and it's further away from the center of that atom. And like I said, we'll get more into it, but there is a reason why, obviously, that these are less electronegative. But fluorine is the highest in electronegativity. You'll sometimes see these rounded, so a lot of times you'll see just 4.0 for fluorine. So this whole thing, the electron negativity it's the tendency of an atom in a molecule to attract the shared pair of electrons towards itself. So basically, it's just saying how likely it is and what amount of force it has to pull in an electron. And fluorine would be the one that has the highest chance of pulling in. Actually, it is the highest to pull in an electron. So this chart here is a 3D version of what we just looked at, and it's just a little bit helpful to see what this looks like as a whole. And you can see it's not exactly like a one-way street here, because you can see like it goes up here and down here. But the main concept of it is that it increases electronegativity going from left to right, and then it also increases electronegativity going from bottom to top. Okay, so you're going to want to remember that because that is on your final. So going this way, higher electronegative, going this way, higher electronegative, and then if it helps, I mean, this is the highest one in the corner, so you have to understand that it's going to go, I can't do it because I don't have two hands, mice, to get to the corner. But basically, if you can remember that this is the highest one here, it's going to be, I believe all the numbers are on your chart when you do your final, but this kind of stuff does come up, so it's good to know how to do this. But it does ask you, I believe it asks you in the final which direction the electronegativity goes, and it's left to right, down to up. And then this just shows like electronegativity in color. So here we've got our elements, and if you look here, it's this line here on period 3 that we're looking at, going from left to right. And you can see here, as you go from left to right, the electronegativity trend is trending up. This chart is to show the how the atomic size affects electronegativity, but we're going to get more into that later. There's got to be better. I haven't gotten through the whole thing yet. I just wanted to get started on this before we start doing some more mathier stuff. So I just wanted to show the diagram here where the atomic size is it says it's decreasing. So anyway, we're going to move on and see if this can all come together better. But this is another chart where it shows an electronegativity trend from fluorine, and then it's going backwards because you've got fluorine and then chlorine, bromine, fluorine, chlorine, bromine. It's going down this way, right? So if you're looking at it in this on this chart, you can automatically tell that it's going to get lower in electronegativity going down, right? So in this case, we did see the trend going up, going from left to right, which was what we already talked about. And then on this one, you see the fluorine is the highest at 4. And then it's going to go down as it goes down the groups. So basically what this is showing is the same thing we already talked about. From left to right, it gets higher. This is the electronegativity. That's what that is. So I don't know why I just lost my train of thought when I did that, but simple concept, left to right, you're going to be getting higher electronegative, and then from up to down, you're going to be getting lower. And like I said, we're going to go deeper into the reasoning behind that later. This chart is really great to have because you're going to be using a lot of this in this course. Electronegativity, we just talked about increasing going this way, decreasing going this way, but there's also different things that happen, like the ionization energy, atomic radius, nuclear charge, and shielding. And shielding is we don't really talk about that a lot, but the ionization energy and the atomic radius and all that we talk about. So if you look at the atomic radius, as you go this way, it's decreasing. The radius is decreasing. And then as you go this way, the radius is increasing. And that affects the electronegativity. So the smaller the atomic radius, the higher the electronegative. The higher, the bigger it gets, the bigger the radius gets, the less electronegative. And that's what I was talking about earlier. There's going to be some stuff we go through that explains that. But if you think about all the shells of an atom when you're doing your, when you're writing out your atoms and they have their little shells and you put their electrons on it, the bigger it gets, the further you're getting from that center, and it's shielding it. But we'll go into that a little bit more later. I'm not trying to confuse you. So we're going to get into ion attraction. It's a very simple concept to start. Like, we all know that negatives fight against each other, and then positives fight against each other, but when you have a positive and a negative, they attract. So the types of bonding are super important. Lindley uses them a lot. They're going to be on your exam. And it's really good to understand the concept behind them if you don't already. So covalent bonds are non-polar or polar. So you can have a non-polar covalent or a polar covalent bond. Okay. So when you look at a non-polar, they have shared electrons. They're sharing electrons. They're still sharing electrons in polar. Non-polar and polar both share electrons. Covalent bonds can be polar or non-polar. They both share electrons, okay? However, when you get to ionic bonds, greedy little negative takes the electrons to itself, which is why you'll see that huge chlorine on one side and the hydrogen's little bitty on the other side. But looking at the covalent bonds, they are atoms. So this is important. If you have an H and an F with no plus or minus over their letters, they are atoms, not ions. It becomes an ion when it has a charge. So you can have an H plus and an F negative, and they would be ions. But if they don't have that charge, they're atoms. Okay? Important concept. So in the covalent bond, the atoms, not the ions, the atoms are sharing electrons. Okay, that's a covalent bond. Now, what makes them nonpolar and polar are their partial charges. So here you'll see your delta negative and your delta positive. Now, it's the balance of the attractive and repulsive forces between these atoms. So if one of them is negatively charged by electronegativity, like fluorine and hydrogen, the electrons will be pulled toward the higher negativity, so more negative. While if they both have equal electronegativity, they would just have a nonpolar bond in the center. It would be very balanced. So it can be polar or nonpolar depending on the atom's electronegativities. And some examples of those are water and chlorine. So if you have H2O, we'll probably look at how that would work out when we do some examples actually. So we won't get too far into it. But we can talk about ionic bonds. So the ionic bond is obviously, like we said, has those charges like H plus and F negative, and they are, whoever has the more electronegative side will grab the electrons, will pull the electrons towards it, and this specific bond is weak. But it's a weak electrostatic force that keeps them bonded together. And we'll get deeper into the examples when we do the mathier stuff. So, ion dipole forces. When you have an electronegative and then a positive on this side, you can imagine that if there are other ions floating around, that the charges here could attract other ones. So in this case, with the positive being on this side, it wouldn't attract a positive cation to it, right? Because opposites attract. So the anion forms an attractive force with the positive end of this molecule, and then they would attach. And then in this case, the cation, cat is positive, an is negative, it forms an attractive force with the negative end. And this is called an ion dipole force. Okay, so this is just another example. I thought this one was prettier, but I like to do more than one for different, like eyeballing, where you can see the plus and the negative and the plus. They're still polar molecules here. These are polar molecules. They're attracting their opposite sign. Okay. So when you're looking at hydrogen chloride, hydrogen is a plus and chloride is a negative. It's going to be pulling the electron toward the more electronegative side, and that makes this bigger. It's like pulling it this way, it's like a stress. So the distribution of electron density in the hydrogen chloride molecule is uneven. The electron density is greater around the chlorine nucleus, which is the small dot, and the black dots indicate the location of the hydrogen and chlorine nuclei in the molecule. I'm sure you can see that. But the symbols for the delta positive and delta negative indicate the polarity of the hydrogen chloride bond. So the polarity is more electronegative towards chlorine. It's not a balanced polarity. Balanced, you know what I mean. So we sometimes designate the positive and negative atoms in a polar covalent bond using the Greek delta, which you'll see a lot, and then the plus or minus sign. And anyway, I think you're getting the point by this time. But we're going to go into some of the electronegativities. This is all on that chart. It's just some of them are rounded. So if we were to go back and look at lithium in the chart, it's 1.0. If we're going to look at beryllium, 1.57, 1.5, 1.57 is a 1.6. So, it's rounded on some of them. But anyway, point is, that's what that is. You have your electronegativity is going to be represented by this cute little X. And then when you do the delta electronegativity, this is showing the change in electronegativity. So what's happening is when you have a lithium and a fluorine come together, you've got a 1.0 electronegativity charge and a 4.0 electronegativity charge. And you just take the higher one, which is 4.0, and you subtract your 1.0, giving you a 3.0 delta X. Okay, so this is going to happen for all your mathy stuff. And this helps you to determine whether you're dealing with a non-polar covalent or a very polar covalent or an ionic compound. Now, ionic compounds or ionic bonds are, they specifically need to have a charge on them. So we'll get more into that as we go. But you can see here, beryllium and fluorine, 4.0 minus 1.6 is 2.4. And then boron and fluorine, are 4.0 minus 2.0, giving you a 2. It's just subtraction, simple subtraction, to give you an idea of what type of bond you're dealing with. So increasing covalent bond character is going this way because as you go closer to 0, so hold on, I'm just looking at something real quick. Okay. Yeah, so increasing covalent bond character is going this way as it's decreasing the charge separation. And then as you're going this way, it's increasing the ionic bond character and increasing the charge separation. So when you're looking at this chart here, 1.7 or greater is ionic. So as you can see here, 1.7 or greater, as you're going this way, it's getting more ionic. And then as you're going from like a higher level to a lower, you're increasing the covalent bond character. So I did some looking up with the hydrogen fluoride because I was confused as if you would like, if you look at the chart, you have a 4.0 fluorine and a 2.1 hydrogen, which gives you a 1.9. And a 1.9 is in some charts is ionic. So it was confusing me, but it does say online that it has some ionic character. That's basically what this is saying. Because here, if you look here, 1.7 or greater, it has ionic listed. So in Dr. Lindley's lecture, he was saying that it's not ionic, that it's a very polar covalent bond between hydrogen and fluorine. And the thing is he's right. It is a very polar covalent because it doesn't have a charge. If you have H and F but no charges on it, it cannot be ionic. It has to just strictly be very, very polar covalent. So that's the difference. That's the important part. It's easily forgotten, I guess is what I'm saying, that it needs to have its charges in order to be considered ionic. So I'm going to pause this and because now it's the mathy stuff. So I'm going to pause it and I'm going to make a new video for math and come back to this one for lecture. Okay, so the next thing he does for his lecture is going to be doing the math part of this. It doesn't seem like he does too much mathy stuff afterwards, so there's no way for me to do another video while this one's still going. So I'm just going to stop this one and label it. Obviously you'll realize that before you get this, so this is probably pointless for me to say this, but yeah, I'm gonna have to stop this so that I can do the math part and then go back to lecture with a new video. Bye.